shifts the Fermi levels towards the valence band and reduces p-type conductivity. This data means that a significant redistribution of intrinsic defects is caused by heterovalent doping, as a result of which a particular type of defects becomes dominant in the perovskite structure, while other defects are negligible depending on the type of dopant. Under standard operating conditions, perovskite materials are highly non-equilibrium thermodynamic state due to electronic excitation induced by either absorbed light or applied voltage. The interaction of free charge carriers of excitons caused by such excitation, which latest defects can significantly change both the type of defects and their energy distribution. In turn,
Andrey, I'm sorry, short question. We see always the same slide. Is it okay?
yes.
Oh, sorry, I'm sorry. Sorry to interrupt you.
In turn, this change can affect both of the electronic and optical behavior of the perovskite materials. In this paper, we present the results of the study of perovskite cesium plumbum bromium-3 plus bismuth crystals by 133 cesium NMR. Both pristine and bismuth plus doped cesium plumbum bromium-3 single crystals were grown using anti-solvent vapor assisted crystallization method. Bromide precursors, as presented in the figure, with different bismuth plumbum ratios were dissolvented in the MSO and kept at stirring and moderate heating condition until formation of a transparent saturated solution. Solution was then filtered and transferred to another container covered with cellulose membrane and placed into a vessel with 20% ethanol solution as anti-solvent. Solution was kept for 48 hours at 40 degrees by centigrade, formed single crystals when crystals with color altered from yellowish orange to dark red, depending on the bismuth concentration. We air dried and stored is desiccators. All surface analysis were performed on freshly colored crystals. Bismuth doped cesium plumbum bromium-3 microdispersed samples as well as undoped cesium plumbum bromium-3 reference samples were synthesized via the chemical precipitation method. Cesium bromium and the plumbum bromium-2 and H-brom were used as a received without further purification. Bismuth bromium-3 were obtained and purified in the laboratory from the corresponding metal nitrates with H-brom. The synthesis of cesium plumbum bromium-3 perovskite powder 2 mol plumbum brom-2 with 1 millimole with 1 millimole cesium brom were dissolved separately in a 10 milliliter ash brom. Then plumbum brom-2 solution was added dropwise with rigorous steering to the clear solution of cesium bromide. 5% excess of lead bromide solution was added into resulting solution to suppress formation of the cesium 2 plumbum from 6 phase. The solution was heated at 28 degrees centigrade until the powder appears. Then the resulting precipitate was collected using a Scotch filter. The residue was washed with a small amount of H-brom, and the unreacted agent was removed. Finally, the sediment was dried under vacuum conditions, only to obtain an orange cesium plumbum brom 3 powder. The same figure. Synthesis of the doped samples was performed in a similar way. Before the synthesis procedure, required amount of either viscous bromine 3 was added to the solution containing plumbum bromine 2 and stirred until complete dissolution. X-ray diffraction measurements with high-resolution reflectometer were used for the crystal phase determination of all studied powdered samples. Structural reference data were taken from ICSD database. Corresponding diffractograms confirm a successful formation of cesium bromine 3 for perovskite phase for both doped and undoped samples. X-ray diffraction of powders did not indicate any side phases. This sample's microstructure was analyzed with the Hitachi S3400N equipped with the Oxford Instruments XMAX 20 extension. Scanning electron microscopy images is backscattered electrons contrast demonstrate single phase both in single crystal in left and in powders in right. Photoluminescence of the powder samples of bismuth 3 plus doped cesium bromine 3 was collected and refocused to an entrance shift of the entrance slit of the Coribe IHR 550. Low temperature photoluminescence spectra of powder samples are presented in figure. The field spectra indicates that bismuth 3 plus doping completely quenches the extonic luminescence and luminescence associated with intrinsic defects. Observed as a shoulder in photoluminescence spectrum of Christian perovskite. The case with the increase of bismuth concentration. New spectral features in photoluminescence spectra are induced by bismuth 3 doping. Samples with bismuth impurity content of as presented in this figure and samples without impurity were used to carry out NMR experiments. The energy level diagram of a spin 7-second nucleus is a strong magnetic field consists of 8 energy levels and 7 single quantum transitions.
Andrey, you have 4 minutes, including questions.
Yes. This is Bruker spectrometer. We used the method mass NMR with these parameters, and the isotope cesium has relatively small quadrupole moment and low ferromagnetic ratio. Simultaneous measurements of the EFG and SCS tensors is expedient to be carried out in strong magnetic field. In the case, the parameters of the first tensor are determined from the orientation dependence in the quadrupole spins. The relatively small value of the quadrupole interaction cesium nuclei made it possible to record the entire spectrum, which magnetically non-equivalent cesium ion at the corresponding values field sweeps. An example of the cesium NMR spectrum at room temperature is shown in figure, and its NMR chemical shift shown in this figure. Cesium NMR spectra parameters of Wismar-doped cesium plutonium bromine 3 compounds were calculated using the Quest software. An example of simulation results is shown in the figure. Conclusions. Cesium atoms in cesium plutonium bromine 3 occupy the one set of structural positions with symmetry. The nearest environment around cesium atoms consists of 8 plutonium atoms located in the positions. In this case, the obtained cesium NMR spectrum fully corresponds to such a structure and has a chemical shift equal 170 ppm with a width of 250 Hz. The set of satellite lines observed in the cesium NMR spectrum corresponds to the non-cubic symmetry of the crystallographic positions of the cesium atoms. An estimate of the quadrupole coupling constant gives a value of 256 kHz. The obtained values of the parameters of the cesium NMR spectrum practically corresponds to the data available in the literature. For the cesium NMR spectra of the doped cesium plutonium bromine 3 plus Wismar samples, a set of satellite lines is also present. However, the peaks of the resonance lines for the central transition in the doped samples are singly shifted down and occupy the region between 117 and 115 ppm. It can be noted that narrow resonance lines in the spectrum are retained in doped samples as well. Thus, the obtained results of the studying the cesium NMR spectra of the cesium plutonium bromine 3 plus Wismar system indicate the efficiency of the doping process with Wismar and indicate the regular entry of Wismar atoms into the crystal lattice of the cesium plutonium bromine 3 compound. Reference to source are presented on this slide. Thank you for your attention.
Thank you very much for your presentation. We have time for a very, very short question, if you have any. So if not, we go because
May I ask
yes,
a small question?
please.
Can
Very
you
short.
show the magic angle spinning spectra again? I didn't understand whether it is due to quadrupolar coupling or it just spinning satellites. We see the central transition average in magic angle spinning, yes, and see a single line. What does this spectra shows?
What does the spectra shows?
We actually see 5 equivalent spectra, and what kind
In
of
this slide,
information?
we can difference between this spectra.
No, as I understand, my question was the
This-
previous spectrum. The pattern, this is
There is a small shift, okay?
Yes, there is a small shift.